I'm coming from a faraway country, Australia, Mr. Morgan, that will deal about hypersonic research at the University of Queensland.
Yeah, I'm going to talk about the research we do in Australia in hypersonics. I'd like to thank the committee for bringing me over here from Australia. It was a long way. I've really enjoyed the stay so far. Everything in Rome has been very hospitable, and the Officers Club are looking after us really very well. We are primarily an experimentally based group. We've been researching hypersonics since 1980, when our founder, Professor Ray Stalker, got Australia's first grant to study scramjets, and I joined him to do this job that was going to take 3 years. And we haven't finished it yet, so I'm still there. Our experiments are based primarily on shock tubes and expansion tubes in the laboratory. In recent years, we've been doing flight testing to try and validate some basic scramjet configurations we developed in the laboratory to see if they work in flight. And we cover a range of activities from aerodynamics, radiating flow, and, as I said, flight tests. The full scope of our activities, I won't go into in too much detail, covers scramjets from the fuel systems, how to make them fly, intakes, integration with flight paths. Thank you. We have a fairly large group. We've got, I just lost the page, right? Yeah.
This is for the slides.
Okay.
Just before you go.
Yeah, okay. I got to try this other one. We seems to be very sensitive. I'll leave it out there. We do CFD as you have to. Our primary work is experimentation. We look on radiating flows, re-entry, TPS systems. And you know, when you start work as a young academic, the students are primarily a time-wasting nuisance, but as you get older, you see that actually the main product we have in universities is the students, and we're very proud, but now we've actually graduated over 100 PhDs in hypersonics, and we're trying to take over the hypersonic world through infiltration of our graduate students. We have nine academic staff members, a large number of students in hypersonics. The facilities, we have the T4 reflected shock tunnel, developed by Professor Ray Stalker. We have the expansion tubes for looking at superorbital flows, which is my own personal line of work. We have a light gas gun. And we have developed, in parallel with these facilities, a fairly large suite of software packages. Within the flight testing, we started off flying HighShot, which was developed by Professor Alan Paul, my colleague of the time, who's now moved on to work for the Defense Services. That was basically a very small space hop to test at about Mach 7 or 8, a simple scramjet combustor. No thrust generated. It was constant area combustor with all the intake was designed to spill any boundary layers, so there'd be no starting problems, just to validate that we can get supersonic combustion in a duct and also at the same time prove that the experiments we do in shock tubes and expansion tubes actually do work. That got expanded to the HiFi program, which we do in collaboration with DARPA, Boeing Company, and several universities around Australia. The HiCAUSE was an American scramjet project we flew, and the ScramSpace was a short-term project funded by a special grant from the government, which had a demonstration flight from Norway last year, which unfortunately crashed, but had some very successful laboratory and outcomes. I'll start with a bit about the facilities. This is the X3, our biggest tunnel, the superorbital expansion tube. It's something like 65 meters long in total, and it can take speeds up to 10 to 15 kilometers per second. This is the nozzle. We've built a family of nozzles to go with it. We've made them out of fiberglass because it's sort of cheap and you can build them quickly. We didn't realize when we first did it, of course, but if the gas going through the nozzle is much hotter than the sun, the light's going to escape. So they glow when you fire them, which caused a lot of trauma for the students standing nearby on our first shot, but they're quite a reliable system. This is a video of X3 firing. If I can get that spot. So typical shock tube work, a lot of work for a millisecond of test flow, and then you have to start again. The other facility we have, a major facility, is T4. This has done more scramjet tests than any other facility in the world. We've done about 12,000 runs since it was first commissioned in 1987. We've accumulated something like 10 seconds of flying time in it, and all our scramjet modules that we've flown have been tested in here. We work on the free piston driven concept for our drivers. I'll say a little bit about that because it's fundamental to everything we do. But this facility is about 44 meters long, and that's a picture from a test section. That's a vehicle shape we tested some years ago. The feature of shock tubes, if you're not shock tube people yourselves, is the test time's very small, and what you've got to do is make sure you don't make it even smaller by having interference from the driver gas. So the conventional shock tube has a primary diaphragm here, shock tube, secondary diaphragm, test section down there, and you burst. Driver has high pressure, high temperature gas if you want to go to high speeds, and you burst the diaphragm, the shock wave rattles down the tube, an XT display, a reflected shock at the end. That's your test gas, of which you have very little. But what you have to be careful of is when the expansion wave, the unloading wave, when you burst the diaphragm, reaches the end and comes back down, it catches up with the flow, and that can destroy your flow before it's even begun. So to avoid this program, you have to make these driver tubes quite long, typically 25 or 30% of the total length of the tube, because they're rated for, say, 1,000 atmospheres pressure typically, and they may take temperatures up to 4,000 degrees. Very expensive bits of hardware. So the way we get around that problem is to use what's called a free piston driver. Our driver gas is contained in a tube by a piston, and we move the piston like a bicycle pump to generate the compressed gas. When you reach a certain amount of compression, the diaphragm bursts, the gas is very hot. You may wonder, well, how does it work if it's such a short tube now? The expansion waves will come running back downstream to kill the flow. Well, if you get the piston speed right, you can have the movement of a piston cancels out the expansion waves from the diaphragm rupturing process, and for a short period of time, you can hold constant pressure. So you have a much shorter driver tube with very good flow quality. So from that point in time, shock wave travels down the tube, does its stuff at the end. This is your test gas going through, and eventually you run out of gas. But if you get all these dynamics right, you can get a reasonable amount of test time, several milliseconds. One thing we've looked at is radiating flows. A problem of studying radiating flows in the laboratory, of course, is they don't scale properly. So if you look at, say, the flow field around a spacecraft, it's radiating here. If you zoom in on this part of the flow, if we do a scale model, if you take, say, a 5-meter flight vehicle, make it, say, 200 millimeters to put in a shock tube, it doesn't scale nicely. So what we have two different approaches. We zoom in on the flow behind the shock wave, do them at real pressures in a non-reflected shock tube, get those. But when we do that, we're not recreating the flow field around the body. We have parallel experiments in the expansion tubes at high density. So this is some sample data taken on the Fire mission, re-entry mission of the 60s. And here we have our sample data here, averaged over a number of shots. This is our flight data. This is our expansion tube data. Fairly nice agreement. We've got velocity on the horizontal axis against a normalized heat transfer parameter. A little bit of scatter in the velocity. We were about 0.5% out in speed, but you can see the overall agreement is nice. It would have been useful information to have before the flight. Of course, when we do that, we just measure total heat transfer. We're not separating the radiative component out. So we developed in parallel with this radiation gauges, which had a glass window to let radiation through, the instrumentation behind the window, isolated from convective heating, was able to separate radiative and convective components. This is sample data from the X3 expansion tube looking at Titan gas, the stuff that's got lots of methane and nitrogen in it. So this is our total heat transfer over here, and separating from it a radiative component, which is only a few percent of the total. We can get reasonably accurate measurement of radiation in these flows. Another problem of looking at re-entry vehicles, of course, in a shock tube is it's hard to get the real temperatures that are associated with flight, thousands of degrees. So one way around that is to preheat your walls with, I'll skip some of these slides here. We can preheat the walls if they're made of graphite just by putting electric charge through them. So our student here has developed a technique for preheating our walls up to about 2,500 degrees. This is a sample of our wall temperature for an ablative experiment. This is infrared imaging of what the temperature is. It's up at about 2,000 degrees. And if you look at it in the flow, you can see this was a simple horseshoe type shaped vehicle. We can look at the spectrometry of the flow in the shock layer, see how it's radiating. We can also look at the spallation. If you watch a video of this, you can see, even though it's only a millisecond of flow, spallation and from the shock layer convecting down the surface. So these are little fragments of carbon graphite that have come off our fragments. So we think that's a useful addition to what we can do, simulating these sort of effects. An important parameter for re-entry, especially if you're looking at high-speed air, is VUV interferometry, and we've recently developed techniques to do that, whereby we have evacuated light paths, enabling us to see what the vacuum ultraviolet radiation is doing in the shock layer. So it's very hard to measure it otherwise because it gets absorbed by any molecular oxygen in the light path. I'll talk a little bit about our scramjet research program. This is run by Professor Michael Smart, my colleague, and he's a pioneer of what's the so-called rest intake of scramjets, where you go from a rectangular to an elliptical cross-section for a good efficiency of structures and for getting a fairly versatile intake that doesn't have starting problems. And this is incorporated with the HiFi program of flight tests, which is a series of 9 flights we're doing. I won't go through them all, but the first one was a cone transition experiment done in collaboration with Roger Kimmel at AFIT in America. We have a family of scramjet experiments that were using different fuels, different configurations, different intakes. This one here is an axisymmetric inward turning scramjet experiment that's been successfully flown. And this one here is what we're planning to fly in a few months, a back-to-back rest inlet scramjets. And we're just trying to validate through a series of 9 flights some of the principles that have been examined in shock tubes and being examined theoretically to show how they'll work. And these are some of the shock tube experiments that go with the flight program. We've got a rest intake set up here and pumping in the fuel, measuring its performance before we fly. And again, we have the same problem earlier speakers have mentioned about getting transition in our scramjet intake to prevent boundary layer separation. We have artificial means of simulating transition or inducing turbulence. We're also looking at how do you package these into something that can fly and be a useful product. And one thing we're interested in doing is not just the cruise of scramjets, but incorporating scramjets into access to space system. And to do that, of course, to get into space, you need an accelerating flight path. You can't just cruise at the same speed. You never get anywhere. And this is Michael Smart's configuration for incorporating a rocket boost to scramjet configuration, a scramjet middle stage, and then a rocket for your final stage, which looks like probably a good practical way of starting scramjet-assisted access to space. This is some of the issues we have with generating turbulence on our intakes, as I mentioned, and these are some shock tunnel experiments we did to try and get the right amount of roughness to give us a nice turbulent intake before we start trying to burn things in a combustor. Part of the associated research is mixing processes involved in a scramjet. You have very little time from injection to the gas going out the exhaust to generate combustion and thrust. And associated with that, we're now flying. We have to worry about the engineering issues of not burning up, protecting things. So we've developed at DSTO in Melbourne a vitiated air facility to give extended duration tests of the thermal protection systems required for flight. This is a manifest of the flights 0 to 9. Most of them have been successful. Unfortunately, HiFi 5, we had a rocket failure at launch. That's funded for a release. It should be flown again early next year. And the final objective is a sustained cruise experiment where we want to fly a scramjet for a minute. I'll finish by talking about another group in Australia that works at University of New South Wales in Canberra. They're a group of academics and researchers who have a shock tube, and they also specialize in instrumentation, particularly instrumentation for flight programs. So they've provided a lot of packages to fly on the HiFi, the HiShot, and the Scram Space programs, and they also do work on the engineering evaluation of the thermal protection systems that fly. One of the items they flew on the scramjet was a diode-based laser sensor, which it's inclined at an angle to the flow. You can generate a Doppler shift, get a velocity measurement, and it can also give you temperature and pressure measurements in flight, which are very useful. Unfortunately, we flew it on the Scram Space vehicle, which crashed. The Doppler shift part of it relies on a significantly high velocity. We have the optical path bounces up and down, so you've got components of the light path going in both directions, so you get a double shift of the peak in the optics due to the Doppler effect. So for it to work, you have to separate the two peaks, and unfortunately our scramjet launched. First stage failed on launch, so we didn't actually get fast enough for the Doppler shift to work, but the pressure and temperature measurements functioned perfectly despite being subjected to 25 degrees in the accidents. But we never actually developed the shifts in these traces that would have enabled speed measurement to develop. Other things they're investigating is the interface between continuum and rarefied flows in their shock tubes, and they've developed a problem with them, of course, experimentally, is the density so low you can't see anything. So they've developed high sensitivity flow visualization systems to help them picture the flow field in a rarefied and transitional flow. These are data from their tunnel. This is validation tests in their shock tube of the flight hardware. So this is the multiple path laser system, which can give you pressure and temperature, and then if you incline it to the flow, as we did in flight, it also becomes a Doppler shift measurement. So this is a function in normal circumstances. You get a separation of what's going on here, the two peaks, and we never got to that speed. We only got single peaks, so we didn't get velocity measurement out of it. But the technique is validated if any people would want to fly this sort of thing in the future. This is calibration of our, okay, that was a timely move. In association with some of our experiments, we've put thermal sensitive paint on the outside of some of the rocket. That could be recovered after the flight and interrogated to see what maximum heating certain parts of the vehicle were subjected to. They also done thermal stressing tests where they heated up part of certain optical components, look through windows. They heated up a bit of carbon to 2,000 or 3,000 degrees, put it in close proximity to the windows to see if it would survive the thermal environment of flight. And it turned out to be a very useful test, very simple but very useful test to check out your materials before you incorporate them. So to summarize, we've got some very good experimental facilities in the country. We've got a flight program which is trying to take the ideas of the laboratory into the flight regime. And there's a broad amount of expertise in the country now for all the aspects that you want of hypersonic flight and of the science of the various aspects of aerothermodynamics, scramjet propulsion, re-entry, etc. And we have 3 major groups in the country. University of Queensland, where I work, University of New South Wales, based in Canberra, University of Southern Queensland, who work very closely with, and of course there's a 4th one, the DSTO, the defence-related research program on hypersonics. So I'll stop there, thank you.
Thank you, Mr. Morgan. There are questions on that?